among all the Math 267 finals we had this semester, this was definitely one of them. And, oh, what a way to put the oomph in, finish up our semester. Well, we should actually talk about the final, work through the problems, and see what the answers are so that our future students can see what they have to look forward to. So here we go. Of course, same cover sheet as before. Well, almost. There's now 8 problems. More fun. Woohoo! So we'll put our name. We'll put it here. Call ourselves Solutions. And away we go. All right. 8 problems. Start with number 1. Solve the following initial value problem. So y prime plus y over x equals 1 over the square root of x squared plus 9, and y of 4 equals 2. All right, well, one of the things we have to figure out is like, what kind of problem is this? What technique are we going to be using? Now, this particular one is in the category of it's a linear first order differential equation. And so we say, hey, integrating factor. So if we go through this carefully, one thing we would say is this is the same as y prime plus 1 over x times y is equal. Now let's make this calculus friendly. And by that we mean we'll rewrite it as x squared plus 9 to the minus 1/2 power. Okay, now that we've written it in this form, we say, all right, the trick is y prime has a 1 in front. Good. And so we come here, and this coefficient is going to be used to make our integrating factor. So we're going to take e to the integral of 1 over x dx. So that's our integrating factor. I'll call that rho. Well, that's e to the natural log of x. Don't need to worry about the plus c that comes from that particular integral. And e to the natural log of x is x. All right, so multiply everything by x, and we'll be good to go. So we have our new equation, x y prime plus y is equal to x times x squared plus 9 to the minus 1/2. And the reason that we're doing this is because when we multiply through, we say, wait, this side is now a derivative. It's the derivative of x times y. So the derivative of x times y is x squared plus 9 to the minus 1/2. And what do? We integrate both sides. All right. Well, that side, it's a freebie. You don't even have to think about how to integrate that. No worries. No worries at all. It's xy. It's really easy to integrate a derivative. All right, so xy. Now, what does that equal? Well, we got to work on this side. Not a freebie. We got to think about it. It's not one of our basic integrals, but it's not terrible. Now, looking at it, we see there's an x here, and there's an x squared plus 9. Now, one of the first things you should always look for, if it's not immediately obvious how to integrate or do something really trivial, is substitution. Substitution is like the most powerful tool. And substitution, we think inside job. Say, hey, if we let u be the inside part, and the only thing that really fits as the inside is that x squared plus 9, then we can say that du is 2x dx. X dx, perfect. And you say, well, what about that too? Don't worry. We have the technology. It's called divide by 2. So 1/2 du is x dx. So you say, all right, then this would become the integral of u to the minus 1/2. All right. And then x dx would become 1/2 du. All right, well, that integral, that's 1/2. Add a 1 to minus 1/2 is to the plus 1/2. And don't forget to multiply by the reciprocal. And here you do need a plus c. Well, the 2's cancel, the 1's are 1's. So you end up with u to the 1/2. But remember, u is x squared plus 9. Okay. Now, since we're past the calculus phase, we can rewrite it as square root of x squared plus 9 and plus some constant c. All right, so that comes over here. Square root x squared plus 9 plus c. Now, there's an initial condition, y of 4 equals 2. So let's use that to help us solve what should c be. All right, so notice this really says x equals 4, y equals 2. So we'll get 4 times 2 is equal to the square root of 4 squared plus 9 plus c. Well, 4 times 2 is 8. 16 plus 9 is 25. Square root of 25 is 5 plus c. All right, so now we know c equals 3. So the last thing for us to do to finish it up, we know c, plug it in, solve for y, and to do that, we divide by x, and so we have our solution is y is equal to the square root x squared plus 9 plus 3 all over x. And we're done. We're done. Well, that's not bad. Whoa, a nice warm-up problem, right? Good. Well, one down. But of course, a lot more still to go. Number 2. A certain species of bird had a population of 500 upon initial observation, and 2 years later was observed to have a population of 750. Assume that the population growth follows the exponential model and says keep your answers in exact form. We don't have a calculator, so it has to be exact. All right, cool. All right. Part A. Set up the initial value differential equation that this situation describes, where P of t is the population after t years. Now, we have like a really key word that tells us what to do. Well, maybe I'll say phrase, exponential model. That gives it away. When you know it's exponential model, that says we follow an exponential function, but it also says that your differential equation has to form p prime equals k times p, and your initial value is the initial population. Well, initial, so we see that it's going to be 500. We're like, what? That was too easy. Well, except we have a small catch. What's k? Okay, so once we find k, we plug k in, and then we really have it all set up. That would be our initial value problem. Okay, so we'll come through. We'll actually solve, and so we have that our population, well, follows the following. P of t is p0 e to the kt. Well, okay, so it's 500 e to the kt. And we're trying to solve for k. Once we have k, we're good to go. Well, what do we know? It says 2 years later, the population is 750. So, P of 2, our population at 2 years, is 750. Well, that's 500 e to the k times 2, because we're putting t equals 2. All right, we'll write it as 2k. Now, divide both sides by 500. 750 divided by 500 turns out to be 3 halves. So we both have a common factor of 250. So 3 halves is equal to e to the 2 times k, or natural log of 3 halves is 2 times k, or we finally come up with k is 1/2 natural log of 3 halves. So put it in, and we come up p prime is equal to 1/2 natural log 3 halves times p, and p of 0 equals 500. So there is our initial value differential equation. All right, perfect, great, beautiful. Now, part B. How long will it take for the population to reach 5,000? Well, this is actually not so bad. Now, what do? Well, we can actually come and use P of t. So we know P of t is equal to 500 e to the k, and that's k, we solve for it. So 1/2 natural log 3 halves times t. And what do we want? Well, we want to get our population to 5,000. So we're going to put P of t to be 5,000, solve for t. All right, so we need 5,000 is equal to 500 times e, this 1/2 natural log 3/2 times t. Well, divide both sides by 500. We get 10 is equal to e to the, again, 1/2 natural log of 3/2 times t. Take the natural log of both sides. Natural log of 10 is equal to 1/2 natural log of 3/2 times t. And finally, well, get t by itself. So we would multiply both sides by 2. So that gives us 2 times natural log of 10. And then divide by this natural log of 3/2. And, well, that's the answer. Without a calculator, we can't do better. We wouldn't want to do better, right? Calculator would just give us a decimal approximation. And our goal is exact. Exact. All right, well, that's number 2. All right, well, that's moving right along. Okay, number 3. A horizontal spring mass system has the following details. There's the mass given, the spring constant given, the damping constant given. Okay, so we have all our pieces here. And there's no external force or friction other than the damping. Now suppose that the mass is displaced to the left, which is negative, because saying left doesn't automatically mean negative. It all depends on orientation. From its equilibrium by 1 meter, and then released from rest. Release just means you just like, boop, let it go. So there's no initial velocity. And now set up an initial value problem to describe the system and solve to find the position x of t, where t is measured in seconds. All right, so we know this is a spring mass problem because, well, it tells us it's a spring mass problem. Now, what we have are there's our various boxes. So something x double prime plus something x prime plus something x equals something. And we have our initial conditions as well. All right. Now, fill in the boxes. And how do we fill in the boxes? Well, we need to understand which each box represents. The first box is for the mass. Think of mass times acceleration as a force. So mass is 2. So we put in 2. The second box is attached to velocity. Velocity is attached to damping because the way the damper works is it affects the force comes from your velocity. The higher the velocity, the more the resistance, the higher the force. So the second box is damping, so that makes this a 10. The next box is Hooke's law, and that comes to the spring constant, so that's 12. The box on the other side is your external forces. Well, there is no external force. That's 0. The x of 0 is where are you initially? Well, remember we said we move to the left by 1. So, moving left is negative. X prime is 0. We release, so there's no initial velocity. So that's 0. All right, so we've actually done the first part of this problem. We have set up an initial value problem. So this is our initial value problem. Let's just rewrite it a little bit more cleanly. 2x double prime, 10x prime, plus 12x equals 0. X of 0 equals negative 1. X prime of 0 equals 0. All right. So that's the first part of the problem. Since they want us to have that, we'll box it. Now, we move on to our next phase, which is, okay, solve. Because, well, we wanted to do it, right? Describe the system and solve. Solve to find the position. Now, this is our favorite kind of problem. Constant coefficients, linear, homogeneous, no, nothing external, meaning, like we said, homogeneous. It's like, beautiful, beautiful. So how do we proceed? Well, we turn this into a polynomial. So we get the following. 2r squared plus 10r plus 12 equals 0. Now you could factor 2 out. That becomes r squared plus 5r plus 6 equals 0. And now we ask the question, does it factor nicely, or maybe are the roots complex? Well, I think, let's see, does it factor? Two numbers that multiply to 6 add to 5? It factors. What? Were they really being nice? That's so like your teachers. So, r plus 2, r plus 3, which means that our roots are -2 and -3. Now, what does that do? Well, it tells us that we have two nice solutions. They're distinct roots, and so our solution looks something like the following. There's some constant a, and then it's going to be e to the -2t, so the -2 coming from our first root, and then there's some constant b, and then e to the -3t. Now that's just generic. So anything that has that differential equation has that form. To solve for a and b, we use our initial conditions. So that's x of t, x prime of t, well, that would be -2a, e to the -2t, and -3b, e to the -3t. So we have, shifting gears ever so slightly, we have our initial condition. So x of 0 is -1, which is a plus b. And x prime of 0, which is 0, is -2a minus 3b. So we're taking advantage of the fact that e to the 0 is 1, so that it's very easy to evaluate. All right, well, two equations, two unknowns. We've done this a lot. You know, if it's one thing we've learned this semester, it's two equations, two unknowns. Here's one thing we can do. Multiply the first equation by 3. So -3 plus 0 would make -3. 3 times a minus 2a makes a, and 3 times b minus 3b makes 0. So we get that a equals -3. And now, since you know a, well, that says -1 equals -3 plus b, or add 3 to both sides, b is equal to 2. So our answer, since we know a, we know b, we substitute in. And we just pay attention to make sure we put in the right value in the right place. So x of t is a, -3, e to the -2t, plus b, which is 2, e to the -3t, and we're done. We found our position function that gives our location for any time t for that differential equation. All right. Wow, we're doing great. We're moving right along. All right, we might finish this test before 2 hours. Woohoo! Well, don't get too excited. We still have some ways to go. Number 4. Find the solutions x of t and y of t of the system of differential equations x prime equals -2x plus 4y, y prime equals -2x plus 2y, with the initial conditions x of 0 equals 1, y of 0 equals -1. All right. Now, you can do this by method of elimination, or if you like, canceling on a variable, but we're going to sort of put on our eigenvalue hats. Say, okay, let's do this by eigenvalue method. So we're going to transform this problem into the following version. X prime equals some matrix X, where, well, what's the matrix? The matrix corresponds to the coefficients. So -2, 4, -2, 2. All right, well, now the fun begins. So we got to find the eigenvalues. So we're going to set 0 equal to the determinant of A minus lambda I, where for reference, when we talk about our matrix A, that's this matrix here. So here's A. So we're going to have the determinant of minus 2 minus lambda, 4 minus 2, and 2 minus lambda. All right, so that would be minus 2 minus lambda times 2 minus lambda, subtract negative 2 times 4. And if we do this carefully, we get lambda squared. Nice. And let's see, we got a plus 2 lambda and a minus 2 lambda. They cancel. And a minus 4, right? And here, plus 8, right? Minus minus makes plus. Minus 4 plus 8 makes plus 4. Now remember, that equals 0. All right, well, what's lambda? Subtract 4. Lambda squared equals negative 4. And that means it's going to be a little bit complex. So lambda equals plus or minus 2i. All right, complex eigenvalues. Well, that's okay. It's all right to have complex eigenvalues. Now, the next step is, once we've identified our eigenvalues, is to transition into finding our eigenvectors. So what we're going to do is we're going to take our A minus lambda I. So let's do lambda equals plus 2i. And so we're going to take our minus 2 minus 2i, 4 minus 2, and 2 minus 2i. And we're going to multiply that by some AB equals 0, 0. And now we want to find a choice for A and B that make this work. Now, it turns out, well, there's going to be lots of choices, but we just need to find one choice. And if you think about this, you might be like, ugh, this sounds complicated. But remember, when we're doing the eigenvalue method, we have two equations, but it's actually one equation. There's redundancy. So what are our two equations? Well, minus 2 minus 2i, A plus 4b equals 0. That's the top equation. And minus 2a plus 2 minus 2ib equals 0. But because there's redundancy, that meaning that these are really multiples of one another. Now, it's a little harder to see when there are complex numbers involved, but I promise you, they are in fact multiples of one another. Okay, well, all right, so what? Well, just knock one out. I'll knock this one out. And then I say, hey, look, all of these are 2's attached. So this is the same as minus a plus 1 minus I times b equals 0. Or we could say, hey, that says a is 1 minus I times b. So our eigenvector is AB is the same as 1 minus I and 1 times the constant b. So this is our eigenvector. All right, good. Now, let's put things together. So we have our eigenvalue is 2i, and our eigenvector, well, remember when we're dealing with complex, it's good to pull it apart. So we'll think of it as 1, 1 plus minus 1, 0 times I. Okay? So in other words, it's like the real part and the imaginary part. And yeah, that's what it is. It's the real part and it's the imaginary part. Okay, now, here's the fun. What we're going to do is, normally we think of a solution is e to the lambda t times that eigenvector. But when we have complex, because of the nature of the solutions, they come in natural pairs. And we can actually take one solution and find the pair of solutions in a nice way. So that's what we do. All right, so let's move this up. And the way we do it is the following. All right, we have the cosine of 2t plus I sine of 2t, and then times that by 1, 1, plus, I'll put the I in front, negative 1, 0. So this part right here is e to the eigenvalue t. And then using some basic facts, de Moivre's formula, sounds very French, de Moivre. And then this is our eigenvector. And now what we do is we multiply it out. And remember, we're going to have sort of two things. So we have the real parts that help make real pieces. Now, take the real times the real, the imaginary times the imaginary, because I squared equals minus 1. And so we end up with our 1, 1 times cosine 2t, and I squared makes our minus, and then we have a, well, there's another minus there, but we'll clean that up later. Minus 1, 0, sine of 2t. Okay, so this is our first solution. Okay, times that by some constant a, plus our second solution. Again, we'll multiply by some constant. Now the second solution, that will come from looking at things where we end up with the imaginary parts. Okay, so we have cosine 2t times that minus 1, 0. All right, great. And then we have that sine 2t times that 1, 1. All right, so this is our solution. Good, good. Now, we actually have some more information. Let's come back to where we were before. Now, when we talk about this system, well, what we know is x of 0 equals 1 and y of 0 equals minus 1. So that says at t equals 0, we should have 1 minus 1. So in other words, we're thinking of the first entry as being 1, and the second entry as being, the first entry as being what it will be the x of t, and the second entry as being what will be the y of t. Okay, so now we come back here. We say, okay, great. Plug in t equals 0. And what'll happen? Well, sine goes away. All right. Well, okay, that happens a lot of time when we're dealing with these things. No worries. And so what we have a times 1, 1, and we have b times minus 1, 0. Or if you like, that's really, well, like we said, that's 1 minus 1. So I'm just copying from the top of the page. You can't see it right now, but I promise you it's still there. And so, say, okay, so we get a minus b equals plus 1. And we have that a plus 0b equals minus 1. Oh, well, that makes it really nice. So if a equals minus 1, which that's what the second equation says, then we have minus 1 minus b equals plus 1. Okay, well, okay, so move the b around. So b has to equal minus 2. All right. Well, we're running out of space. That's okay. We should have some scratch paper somewhere. Well, I brought some scratch paper with me. Haha, different color, but that's okay. It's still paper. Paper is paper, right? I think that's still true. All right, so let's see what we have here. All right, so let's update. We know our solution has the form minus 1 times this expression. Well, let's start collecting things. So that'd be cosine 2t minus minus makes plus sine of 2t. And then downstairs 1 times cosine of 2t. And then minus 0 sine of 2t. Okay, so that's A. And then this one just collapsed into a vector. And then B makes minus 2, but we'll do the same thing. So it's minus cosine 2t, so right? And then plus sine of 2t. And then we have 0 cosine 2t and sine of 2t. All right. Put this paper aside. And, well, we're almost there. Just a little bit more cleaning up. So let's put this all together into 1. So there's a minus cosine 2t, a plus 2 cosine 2t. So minus 1 plus 2 leaves us with a cosine of 2t. A minus sine 2t minus 2 sine 2t leaves us with a minus 3 sine of 2t. Downstairs we have minus cosine 2t and minus 2 sine of 2t. All right. Now, we're almost done. But remember way back when we started this problem a few minutes ago, we said, oh, we're putting it into a vector. So what happens here is that this vector, the first entry was the function x of t, and the second entry is y of t. Now, you probably can't tell from my handwriting, but this x is a bold x, where this x is not so bold. And so, since we're after x of t and y of t, the last thing is just to say, all right, pull it out of the vector. So our final answer, x of t, is cosine of 2t minus 3 sine of 2t, and y of t is minus cosine of 2t minus 2 sine of 2t. And we're done. That's it. That's our answer. Ah, nice. Nice. That took a little bit of space, but it didn't require so much, it's not space because like, oh, there's so many complicated things. It's just like, well, it takes a while to write things down. But the basic ideas aren't so bad. It's like, well, complex eigenvalues, find the eigenvector, break things up into our two solutions, solve, and away we go. That's that problem. Which means we're halfway there. Woohoo! All right. Coming on round 2. So we have the system of differential equations. X prime equals ax, with a equals 2, 0, minus 1, 2, and x of 0 equals 1, 2, says first, find the matrix exponential e to the at, and then use it to find the particular solution x of t. All right. Well, first, find the eigenvalues. Okay. All right. So we're going to take 0 equals the determinant of a minus lambda I. Okay, that's the determinant of 2 minus lambda, 0, minus 1, 2 minus lambda. And, well, that's actually pretty easy. It's 2 minus lambda squared, subtract 0. So, aha, our eigenvalues are both 2. It's a repeated eigenvalues. And now we're like, whoa! Because there's a quick way to do this. Now, we'll do it the non-quick way, but here's the quick. Once we know we're in repeated eigenvalues, we say, hey, e to the at is equal to that eigenvalue, e to that eigenvalue t, and we'll fill in the pieces here in a second, times the identity matrix, and plus a minus lambda I times t. Essentially, it's like we're taking that, expansion for e to the at, and we're just contracting it because what happens is the next terms are all 0. Okay, so in our case, it would be e to the 2t, because lambda equals 2. The identity matrix is 1, 0, 0, 1. And a minus lambda I, well, that's a minus lambda I there, but we just put in 2. So that's 0, 0, minus 1, 0 times t. Well, which says what? Well, it says e to the at is going to be e to the 2t, that's the first entry, and then 0, and let's see, the next entry, 0 minus t, so minus t e to the 2t, and e to the 2t. All right, so that's e to the at. Now, how do we use it to find the particular solution? Well, that is actually pretty fun too. So we have that x is equal to e to the at times x of 0. So that would be e to the 2t, 0, minus t e to the 2t, e to the 2t, times 1, 2, because that's our initial condition. And we do our multiplication, and we get, okay, e to the 2t plus 0, that's e to the 2t. And then we have minus t e to the 2t, and plus 2 e to the 2t, and we're done. All right, so that was the quick way. Let's do, I don't want to call it the slow way, so we'll call it the non-quick way. Now, the thing is, the non-quick way is just, how do you find that? Okay. Well, here what happens is we know we're in the setting, repeated eigenvalues, a mildly interesting matrix, which means we have the missing eigenvector case. All right, so we need to focus on our a minus lambda I, which is the matrix 0, 0, minus 1, 0. And we're going to go through 2 rounds. So the first round, we have 0, 0, minus 1, 0 times some vector AB, and we want to get out 0, 0. Okay, so we have to find a vector that does that. That's going to be an eigenvector. Now, what does this say? It says 0 plus 0 equals 0. Well, that's true. Minus a plus 0 equals 0. Oh, okay, so again, 0 plus 0 equals 0, minus a plus 0 equals 0. Well, the first equation tells us nothing. The second equation tells us that a has to be 0. So I say, oh, okay, so this tells us that our solution AB looks like 0b, or if you like, that's b, 0, 1. So here's our eigenvector. Our eigenvector is 0, 1. Now, round 2. We say, all right, since that works so well, we need to find something where c times d, vector cd, equals 0, 1. And anything that makes that work will be fine. Well, the first equation, again, 0 plus 0 equals 0, not too big of a surprise. And then the second equation says, hey, minus c plus 0 has to equal 1. Oh, well, that's great. So what works? Well, c has to be negative 1. Now you might be saying, wait a second, Steve, I thought you said there were infinitely many correct answers. And there are. Because what's true about d? It can be anything you want. And we say, well, let's make it the simplest thing that we can, 0. You can't get simpler than 0. 0 is a friend. That's one of the things we learned in this class. We say, okay, great. So we can take CD and we'll make it negative 1, 0. All right, so here's our generalized eigenvector. All right. Great. Well, now what? Well, now we have two solutions, and so we say, hey, our solutions to our differential equation are the following. And I'm going to switch colors here. I like being colorful. It's who I am. Yep. And so we have our solutions to our differential equations. Well, there's some constant a times e to the eigenvalue t times our eigenvector, plus some constant b, e to the eigenvalue t times, well, t times our eigenvector, plus our other piece we just found, that minus 1, 0. Okay, well, this is really the same as a times 0 e to the 2t plus b, and then we have, if we clean it up, we'd have minus e to the 2t and t e to the 2t. All right, so those are our two solutions. That's not e to the at, but we're getting close. We're getting close. Remember, once we get to this point, the rest of it's the same. So we're still in that non-quick way of finding our e to the at. So here we go, more scratch paper. It's always okay to use scratch paper to do your work. A pro tip, don't use markers when taking an exam. Pens and pencils, you're able to write a lot smaller. And so if you want to avoid scratch paper, pens and pencils. But take it from me. I've been taking tests for a long time. All right, so what happens next is we make a vector phi of t. So we take our two solutions and we pack them in. 0, e to the 2t minus e to the 2t and t e to the 2t. And now we find phi of 0. Well, all right, that's 0 minus 1, 1, and 0. And the next thing is we find the inverse. And so what is phi of 0 inverse? Well, it's 1 over 0 minus minus 1. That's nice. And now you flip the diagonals. Okay, so it's now 0, 0 on the diagonal, whereas before it was 0, 0. So, interesting. And then we change the signs. So minus 1, plus 1. And as always, if you have any doubts, multiply these two together. But it's not too hard to check. It does indeed work. Okay, now why are we doing all of this? Well, it's our last step because we have the following fact. Here we go. E to the at is equal to phi of t times phi of 0 inverse. So that's 0 minus e to the 2t, e to the 2t, and t e to the 2t times 0, 1, minus 1, 0. And let's just carefully work it out. No need to rush. 0 e to the 2t. All right. And 0 and 0. Okay, great. 0 minus t e to the 2t. And e to the 2t and 0. And there we go. There's our e to the at. And so that we can actually believe it, let's check the two answers. And they're the same. Woo! All right. Now, let me pause, and I'll make a quick comment. A lot of people are like, I want to do it the quick way, but they didn't memorize the formula correctly. If you're going to do something the quick way, memorize the formula. You can't do something unless you are confident you can do it correctly. So make sure you have it nailed down. By the way, there's some beautiful checks, especially for 2x2s. to say, did I get this right? So the checks are plug in 0. Do you get the identity matrix? I mean, you do 1, 0, 0, 1. Take the derivative. So in other words, 2e to the 2t, 0, some stuff here, product rule, and plug in again 0. Do you get the matrix you started with? And if the answer is yes both times, you're in good shape. If the answer is no, uh-oh. Check your work. Something has happened here. So, all right. And, well, that's number 5, which means we're up to number 6. Woohoo! My problem! This is me! And you're probably thinking, yes, Steve, you have many problems. But I'm actually kind of excited about this. Of course, it's the Laplace transform. So there is a table. We might refer to it. And this is the two-parter. And this one feels like it really is like significantly, like, wow. Let's see how it goes. Part A. Find the Laplace transform of the integral from 0 to t of tau sine of 3 tau e to the tau minus t d tau. And it says, all right, write your answer as polynomial over polynomial. All right, great. And you say, okay, let me just pull up my table here, and I'll find a place where there's an integral sign somewhere on here. And there's no integral sign. Is anywhere on this table? You're like, Steve, you punk! Gah! Or am I? Okay, so here's the thing. This is testing you. Of course, it's a test. We have to test you on this entry. Now, that entry is what? F star G. Well, what is F star G? F star G is convolution. So, we didn't give you the formula for it, but it's the following. F star G of t is the integral from 0 to t of f of t, g of, not t, tau, g of t minus tau, d tau. That's convolution. You're like, whoa, well, that looks a lot like what we're doing. It does. It does. And see, once we understand that, we start saying, oh, let's put on our convolution hat. Okay, so what we have the integral 0 to t of tau sine of 3 tau. And then we have e to the tau minus t d tau. Now, you might say, we were so close, Steve. We see that the function which only depends on tau, but now you have tau minus t, not t minus tau. Easy fix. So this is the integral 0 to t of, and just to help emphasize, tau sine of 3 tau. And now, here we can pull out a minus. So minus t minus tau. And now we're like, so what this really is this is the convolution of the function t sine of 3t with the function e to the minus t. All right. Now, here's the great thing. If we go back to our table for just a second, if we have the convolution, it says take them each individually. Now, do we have t sine 3t? Yes, we do. Do we have e to the minus t? Yeah, it's down here at the bottom. So, t sine 3t, okay, that's a equals 3. So it's 2 times s times 3. That's 6s over s squared plus 3 squared. That's 9 quantity squared. So this part will go to 6s over s squared plus 9 squared under Laplace transform. So that's from the table, a equals 3. All right. Now e to the minus t, this will go to 1 over s minus minus 1. Of course, minus minus makes plus, And remember, the rule says these multiply. So our final answer is 6s, divide that by s squared plus 9 squared times s plus 1. And we're done. That's part A. A lot easier than it looks initially, isn't it? Well, the important thing is to say, hey, and understand the ideas. Understand what's being tested. We see convolutions on the list. We better know what convolution is. And if we do, life is good. If we don't, uh-oh. But of course we did. So we're happy. Part B. Find the inverse Laplace transform of this expression, 3s minus 11 e to the power of 12 minus 3s over s minus 4 squared. And simplify your answer as much as possible. Now, when you see something that says simplify your answer as much as possible, it's sending you a clue. The answer is simple. Well, it can be made simple. So we should be suspicious that if we get to a certain point, it's like, can this look simpler? And probably the answer is yes. And so if our answer doesn't look simple, things went wrong. But let's talk about what we're going to do here. Now, the first thing is to say, hey, how does this work? Well, every single problem finding inverse Laplace transform really breaks down into sort of two parts. You have a partial fractions problem, and then maybe an e to the minus something s. That's it. They all look like that, every single one. So our partial fractions problem is 3s minus 11 over s minus 4 quantity squared. Now over here we have e to the 12 minus 3s. Now be careful here. The 12 minus 3s isn't on the chart, or if you like, it's not on the table. It's always like e to the minus as, not e to the something minus as. So how do you handle that? Well, the answer is we use this sophisticated idea that says, oh, this is e to the 12, e to the minus 3s. So e to the 12 is a constant. It just will follow along. All right, so first things first, partial fraction decomposition. Okay, so we have 3s minus 11 over s minus 4 squared. Well, that's something over s minus 4 plus something over s minus 4 squared, right? You work your way up. Clear your denominators. And so to help clear our denominators, we would multiply both sides by this quantity of s minus 4 squared. And doing that leads us to the following equation. 3s minus 11 is equal to a. And then here, 1s minus 4 will cancel. And then in the second one, they both cancel. So plus b. Now, we can do this in a couple different ways. We can choose some nice values, or we can expand and group coefficients. They're both quick, actually. They're both very quick. Some nice values, you can choose s equals 4, and then that automatically gives you that b equals 1. Once you have that, plug in s equals 5, and you can solve for a. Another way you can do it is if you expand coefficients. This is a times s plus b minus 4 times a. Well, the coefficients on both sides have to match. So that says, a has to be 3. And of course, b minus 4a minus 11. All right, so if a is 3, we say, well, b minus 12 is minus 11. And so we come up with the conclusion that b has to equal 1, which we already mentioned if you plug in 4 at the very beginning. Okay, so let's update what we have. So as with almost every problem involving Laplace transform, most of the work happens before the transform. It's processing it, cleaning it up, getting you ready to carry it through. And then once you've carried it through, Then you have a little bit of cleanup at the end. All right, so we're going to rewrite our original expression. We still have e to the 12. Well, that's all the way out in the front, so we'll just leave it in the front for right now. Hopefully that will clean up. We suspect it will, but we don't know yet. And now we have a over s minus 4. Okay, so we have 3 times 1 over s minus 4, and okay, and then we have b, which is 1 over s minus 4 squared, and all this times e to the minus 3s. Now, let's look at our table. First off, 1 over s minus 4. That shows up, that would correspond to e to the 4t. So, this part right here would normally be e to the 4t, and I'll come back to what I mean by normally. 1 over s minus 4 squared also shows up, t e to the 4t. All right, well, that's looking great. T e to the 4t. And now this part right here says shift. Right? Whenever we see an e to the minus as, there's a shift involved. And in our case, we have a shift by 3. Okay, so now we're ready to say our transform. Well, inverse Laplace transform. Here we go. It is e to the 12. Then 3 e to the 4. Remember, we have to shift everything by 3. So what that means when we talk about the shift by 3, so instead of t, we're going to talk about t minus 3. So 4 times t minus 3. And then plus, here, this t will become t minus 3, e to the 4 again, t minus 3. All right. And then the last thing is we have that on-off switch, u. Okay, now this is in answer to the inverse Laplace, but we haven't finished the problem because remember, it told us simplify as much as possible. Okay, so what are some things we can do? Well, notice these are both common. We have 3 and t minus 3. So that's great. So we can put these together. 3 plus t minus 3 makes 12. Sorry, excuse me. 3 plus t minus 3 makes t. I'm getting ahead of myself. I saw a 12 for there. Here, you can factor the 4 through. E to the 4t minus 12 and u of t minus 3. Okay? But notice we can add the exponents. Here's a 12. Here's a minus 12. When you put them together, what happens? Cancellation. So we have just t, e to the 4t, and u t minus 3. And that is very simple. We couldn't hope to get much simpler than that. And so, we're done. We're done. Ah, beautiful, beautiful. All right. Well, that's number 6. Moving right along, which brings us to number 7. Okay. Solve the following differential equation using Laplace transform. So, y double prime minus 4y prime plus 8y equals 8. Y of 0 equals minus 1. Y prime of 0 equals 2. Okay, well, that's great. No big surprises here. You know, there's no like turning things on, turning things off. We could solve this without Laplace transform, without too much effort, but we're going to follow the rules. It says use Laplace transform. Okay, so here we go. So we're going to take the Laplace transform of both sides. So Laplace transform y double prime minus 4, Laplace transform y prime plus 8 times Laplace transform of y is equal to the Laplace transform of 8. Okay, so we're just throwing Laplace transform. And now, of course, our table helps us because it says when you have, say, a second derivative, it's s squared times the function you're after minus s x of 0 minus x prime of 0. When it's the first derivative, it's s, the function you're after, minus x 0. Of course, the x's become y's, but other than that, the sentiment is the same. So this first piece becomes s squared y of s, subtract s times what happens at 0, minus 1, and then subtract what happens to the derivative at 0, which is 2. Minus 4 s y of s, subtract what happens at 0, which is minus 1. And plus 8, well, that's just what we're after, y of s. And the Laplace transform of 8, well, it's really the Laplace transform of 1, which is, no surprise, the very first thing on our table. It's 1 over s. Okay, well, times 8. So that's equal to 8 over s. Okay, well, great. Now, what do? Well, we clean it up. Okay, so we can say, okay, this is s squared minus 4s plus 8 times y of s. And, well, we have a plus s, so we'll write that down, minus 2, and here there's lots of things going on. So minus makes a plus, and there's another minus, so minus 4 minus 2 makes minus 6. All right, good. And that equals 8 over s. And, all right, so we have s squared minus 4s plus 8 times y of s is equal to 8 over s minus s plus 6. If we wanted to, why not? Let's put it all together. Sometimes it makes sense to put it all together if you're anticipating a partial fraction where things don't clean up in a nice way. And then we'll just do one partial fraction instead of having to do 2. Okay, so that's equal to, well, it'll become 8 plus 6 times s, subtract s squared, all of that over s. All right. So, finally, y of s is 8 plus 6s, excuse me, 8 plus 6s minus s squared, all over s times this s squared minus 4s plus 8. Now, we probably should make a comment here when we talk about s squared minus 4s plus 8. So let's make that comment. Does it factor nicely? And if it doesn't factor nicely, you should say, I don't see it factoring nicely. So do completing the square. So s squared minus 4s, if I wanted to complete the square, divide the middle term by 2, minus 2, square that is 4. And that leaves us 4 short. So it's s minus 2 squared plus 2 squared. So this really says complex roots, which means we're going to have cosines and sines showing up in some way, shape, or form. But for right now, let's not worry about that. Let's keep going. So we really have 2 pieces. So we're saying, all right, let's run our partial fractions. So this is equal to something over s plus some bs plus c over s squared minus 4s plus 8. And we have the upstairs in that form because the downstairs is an irreducible quadratic. It doesn't factor without doing complex roots. And so that's what we saw from this little computation here. Okay. So we just have to figure out A, B, and C. So now do a little detour here, partial fractions detour. And what we do is we just think about this expression, clearing off our denominators. Well, we'd have the following. We would get that 8 plus 6s minus s squared is equal to A, and then the other piece, s squared minus 4s plus 8, plus b times s plus c times s. Now, you could plug in s equals 0, and if you do that, you'll get that a equals 1. Or you could say, let me just expand and group by powers. So if you look at the s squared, you get a plus b. If you look at the s, well, you get minus 4a and plus c. And if you look at the constant term, you get 8a. And now you just go through and compare it to the other side. So the constant term is 8. What's in front of s is 6. And what's in front of s squared is minus 1. So we just start working our way through. And 8a equals 8. Well, we said, before we even start, a equals 1. Now come here. A equals 1. 1 plus b equals minus 1. So that says b equals minus 2. Come here. Minus 4 plus c equals 6. So c equals 10. And there we go. That's it. That's it. All right. Well, that's not so bad. So, updating. We have that y of s is equal to 1 over s. And then we have b times s plus c. So plus minus 2s plus 10 over, and I'm going to write s squared minus 4s plus 8 in this format right here. So that's s minus 2 squared plus 2 squared. Now, in order for us to really apply our table, notice the s minus something squared plus k squared. That fits in to this part of our table. Okay, well that's great. We like that it fits into our table, but we have to be careful here. Notice that upstairs, it's not s, it's s minus a. So, here's what we're going to do. We're going to rewrite this so that it looks like s minus a. So we're going to have this as plus, and then it's going to be minus 2 times s minus 2. And we have s minus 2 squared plus 2 squared. And now we say, well, what goes here? Well, we're at plus 4. We need to get to 10, so we're short 6. All right. All right, we're almost there. We're almost there. And I know you're thinking, oh, more scratch paper, Steve? I don't think so. I think we'll make it. So what do we have? We have 1 over s. And now cover the 6. And I can pull out the minus 2. And then we have s minus 2 over s minus 2 squared plus 2 squared. Okay. Now, the next thing, table, is a constant upstairs, but we want that constant to match the k. Now, k should be 2, so we really want a 2 upstairs. So the 6, we'll think of as 3 times 2. So we're going to pull out a 3, and then we're going to have 2 over s minus 2 squared plus 2 squared. And now we're like, wow, perfect. Each one of these pieces is on our table. So y of t is 1 over s is 1. So we get 1 minus 2. Okay, s minus 2 over s minus 2 squared plus k squared. So a equals 2, k equals 2. E to the 2t cosine 2t. So e to the 2t cosine 2t. Okay, that's that part. Plus 3. And the last thing is k over s minus a squared plus k squared. A equals 2, k equals 2. So e to the 2t sine 2t. So plus 3 e to the 2t sine of 2t. And we're done. That's it. That's our answer. See, I told you we'd make it. We fit it in. So that one, we fit it on a page. Whoa! That's so cool. That's so cool. All right. Well, in some sense, they gave us pretty nice conditions to work with, so that at the end, it would work out kind of nicely. You know, when you see a nice answer, you're like, probably right. You know, we expect answers to be nice. All right, well, that's number 7, which means one more problem, right? Number 8. Find the recurrence relation for the coefficients in a power series solution, and I mean this is a power series solution, of 3y double prime plus xy prime plus 4y equals 0. And if y of 0 equals 2 and y prime of 0 equals 1, find the first 4 terms of the series. Okay, great. Now, well, we start as we do pretty much any problem that involves series, and we say, okay, we have y, and what we'll need is we'll need y prime and y double prime. Okay, so y prime, that's a summation, n equals 0 to infinity of n c sub n x to the n, and y double prime, that'll be the summation n equals 0 to infinity of, oops, I forgot my minus 1, of n times n minus 1, c sub n x to the n minus 2. Okay, so we have our y prime, y double prime. So we put those expressions in. So 3 times our sum, 0 to infinity, n times n minus 1, c sub n x to the n minus 2, plus x times our y prime, our sum n equals 0 to infinity, and c sub n x to the n minus 1, plus our 4 times our y, sum n equals 0 to infinity of c sub n x to the n. All of that equals 0. All right. Well, good. Now we follow the flow. These patterns always have a nice flow. The constants are going to move in. So that's what we're going to do. Move all these constants. Well, I shouldn't say constants. X isn't a constant. I should say coefficients. Coefficients move in. And so now we have the following. This will become the sum from n equals 0 to infinity of 3 n minus 1 c sub n x to the n minus 2. The next case, because it's x, the only thing that will happen is it'll become n c sub n x to the n. Oh, that's kind of nice. And plus, in the last part, the sum n equals 0 to infinity of 4 c sub n x to the n. And of course, that all equals 0. Now, let me pause here and say, you know, this sum that starts at 0, we can have it start anywhere. Well, not start anywhere. It doesn't have to start at 0, because notice when you plug in 0, it goes to 0. When you plug in 1, it goes to 0. So, let's change it to 2. All right. Now, these look pretty good, x to the n. I like that. I like x to the n. It's something I feel comfortable with. This is x to the n minus 2. I don't like that. So what I want to do is I want to have all the powers match. So I'm going to do some re-indexing, shifting if you like, substitution. There's lots of ways to call this. So here, I'll do something I call L equals n minus 2. And for these ones, we'll just leave them as they are. Or if L equals n minus 2, that's the same as n equals L plus 2. So notice, because we changed from starting from 0 to starting at 2, L starts at 0. Okay, so we have the sum starting at 0 to infinity of what? Well, 3 times L plus 2 times L plus 1, C sub L plus 2, x to the L. Okay, plus, well, the other sums, they're not changing, we're just changing the symbol. But changing the symbol doesn't change the sum, and so it's still the same sum, just written in a slightly different way. That's kind of what math is. Math is just saying, hey, let's take this expression and write it in a slightly different, but somehow simpler way. And then keep doing that again and again and again. And at the end, we're like, wow, this final way is so easy for us to write. We know it. And waha, we solved it. But we're like, what? You just did lots of simplifying. Exactly. That's what math is. Lots of simplifying. Okay, so we're happy. Our sums all start at the same place. We all have x to the L. We're going to put it all together in one sum. One big happy sum. So sum from 0 to infinity of, okay, so we're grabbing our coefficients, 3 L plus 2 times L plus 1, C L plus 2, plus L C sub L, plus 4 C sub L, and all of that times x to the power L equals 0. Well, thinking of these as polynomials, they're two equal polynomials. Well, the only way two polynomials can be equal is if their coefficients are equal, which means that this expression has to equal 0. And that's the whole crux of this approach. All right, so we're almost to our recurrence relationship. We're practically right there. See, it says 3 times L plus 2 times L plus 1, C L plus 2, plus, and then since they're both C sub L, L plus 4, C sub L equals 0. And, all right, well, move this across, divide, and we come up with the following. C L plus 2 is equal to minus L plus 4, divide that by 3, times L plus 2 times L plus 1, C sub L. All right, so that's part of our answer. Now this is our recurrence relationship, and we'll say this holds starting at 0. Okay, now let's make some other notes. It says what? We found the recurrence relationship, so that's done. And it says, look, suppose you know y of 0 and you know y prime is 0, find the first 4 terms. Now y of 0 and y prime is 0 are telling us the start of the series. So we say, aha, we can say the following, C0 is y of 0. So that's equal to 2. C1, well, that's y prime is 0. And so that equals 1. Now, how do we go from there? That's where our recurrence relationship kicks in. So C2, we come here and say, well, start at L equals 0. So L equals 0, so we would have minus 0 plus 4 is 4. And then we have downstairs 3 times 2 times 1 times C0. Okay, well, that's not so bad, because we know C0 is 2. Okay, so really we have the 2's cancel, so we end up with minus 4 over 3. So I'm using the fact that C0 equals 2. All right, great. Well, a little space left. That should be enough. We can get C3. Okay, now that would be plug in L equals 1. So 1 plus 4 means 5. Then we have 3 times 1 plus 2 is 3. 1 plus 1 is 2. And then times C1. But we know C1 is 1. So it's minus 5 over 3 times 2, which gives us minus 5 over 18. And remember, what are we looking for? We're looking for the first 4 terms. So what do we have? We have 4 coefficients. That's 4. So we actually don't need to go any further. So we can say, aha, the first 4 terms, well, C0 plus C1 times x, so 1 times x, plus C2, which would be 4/3 times x squared, and C3, which would be minus 5 over 18 x cubed. And there's the first 4 terms. Done. Done. All right. And we finished it. And that took us a lot less than 2 hours. Of course, you can imagine if you're in a test, stress adds a few minutes to it. All right. Now you might say, hey, Steve, this is the end. Do you have a bonus problem for us? I do have a bonus problem. Yes, because there was a 268 exam which had 3 of the problems the same, but 1 other problem. Let's do that problem too. Bonus fun. Okay, here we go. Use Laplace transform method to solve the initial value problem. Y double prime plus y equals f of t. Y of 0 equals 1. Y prime of 0 equals minus 1. And f of t is 1, and from 0 to 1, and 0 otherwise. Now, what is that saying? Well, it says, hey, it starts off as 1 and then goes down to 0. Okay, now you might say, okay, well, what's this function? Well, the key here is to say, if this is our function, is to rewrite this in terms of things we're more comfortable with. And in particular, we say, f of t is initially 1, and then there's a transition at 1, so there's a u of t minus 1, which says, we're flipping a switch at time 1, and what we do is we want to cancel it, so it's 1 minus u of t minus 1. Okay, so that's our f of t. All right, well, now I'm not going to give too much commentary because this is very similar to what we did before. So we have our y double prime plus y is 1 minus our u t minus 1. Laplace transform of y double prime will be s squared y of s subtract s times y of 0, and then subtract y prime of 0. So that's y double prime. The transform of y double prime. The transform of y is y of s. The transform of 1 is 1 over s. And the transform of the unit step function, t minus 1, that is on our sheet. It would become e to the minus s over s. So there's, whenever we see exponential inside there, we think, some on-off switch occurred. So e to the minus s over s. Okay, so, well, now what? Well, now we'll move stuff across. So we have, this is really s squared plus 1, y of s is equal to, well, s, this negative s comes across as positive s, and minus 1 plus 1 over s, and I'll say this is minus 1 over s e to the minus s. So we can say that y of s, just divide everything. S over s squared plus 1 minus 1 over s squared plus 1 over s times s squared plus 1 minus 1 over s times s squared plus 1 and e to the minus s. Now these are actually okay. S over s squared plus 1, 1 over s squared plus 1, thumbs up from us. We like those answers. Or I shouldn't say answers. We like those functions to work with. But we have other pieces that we have to figure out. And so in particular, they're both the same. So we only have to do partial fractions once. All right, so detour. So 1 over s times s squared plus 1 is something over s plus b times s plus c over s squared plus 1. Clear out our denominators, and we get, 1 is equal to a times s squared plus 1 plus b times s plus c times s. All right, well, at this stage, we have to do a little bit of work, just a little bit, just the right amount. We could put in s equals 0. If we do that, we come to the conclusion a equals 1. But in this case, we'll probably be just as fast just to group coefficients. So for s squared, we have an a and a b. For s, we just have c. And for a constant, we just have a. And now we say, well, wait a second. Our constant term has to match. So this has to be 1. The in front of c has to match, that has to be 0. And a plus b has to equal 0. So now we're like, well, that's pretty slick. A has to equal 1. B has to equal minus 1. And c has to equal 0. All right. So we've done our partial fraction decomposition. Yes? Indeed, we have. So let's mark that off. Back to our problem. So cleaning up, we have y of s, keep going, is equal to s over s squared plus 1 minus 1 over s squared plus 1. And this 1 over s times s squared plus 1, well, a over s, okay, so a is 1, so plus 1 over s. And then b times s plus c will become minus s, so minus s over s squared plus 1. And then we have this other stuff. Well, we can put the minus through, so plus minus 1 over s and a plus s over s squared plus 1 e to the minus s. And at this stage, we make a quick little note that says, oh, cancellation, you shouldn't have. Or maybe you're thinking, you should have done that a lot sooner. Okay, maybe. But let's talk about each one of the pieces. 1 over s is on our table. That will go to 1. 1 over s squared plus 1. That is also on our table. And, well, maybe not as quick on our feet. But 1 over s squared plus 1 is sine of t. So that goes to sine t. 1 over s goes to 1. S over s squared plus 1. Again, it's on our table. And that is cosine t. So that's cosine t. And finally, this e to the minus f means we have a shift by 1. All right, so let's put this all together. So our final answer, y of t is equal to, well, we'll take the 1, subtract sine of t, and then plus this other part here, well, which is cosine, but it's not t. Shift by 1 means it's t minus 1, and then we're going to subtract 1, right? So we'll take the minus 1 plus cosine t. We just change the order, and remember, shift by 1, put that t minus 1. And then don't forget, we also need to hit the on-off switch, u of t minus 1. And that is it. That's the answer. Wow, that was fun. It was. It was a good, nice, fun problem to work on. A nice cool me down. All right, I hope you did well. Hope you did well. Or if you're preparing, I hope you're going to do well, because that's what we want. We want you to do well. Okay, take care.